everyone. This is the 19th lecture in the series, Mathematical Methods for Economics. We have been talking about limits in the last couple of lectures. And in today's lecture, we will now build on this discussion further and use limits to introduce a new concept, the concept of an asymptote. In fact, I've mentioned in earlier videos as well, an important objective of this first part of the series that you're doing is for you to be able to draw the graph of a function with certain key pieces of information. So our objective in this course is, as teachers, is to get you acquainted with certain techniques, certain pieces of information that you would need to draw the graph of a function. Obviously, it may not be accurate if you're drawing it yourself, but you should get the larger picture in place. And one crucial piece of information that goes into drawing graphs of rational functions in particular, relates to asymptotes. So let's take a look at asymptotes today. Let me first give you a bit of a roadmap for what we're going to talk about today. We'll start by introducing the concept of an asymptote. So note the spelling and the way you pronounce the word. And then after telling you about what the concept involves, I'm going to just break up the lecture into three parts. I hope time permits us to do all the three parts. So I'll break up the lecture into three parts, and in the first part, we will talk about vertical asymptotes. In the second part, we'll talk about horizontal asymptotes. And in the third part, we will talk about oblique or slant asymptotes. So this is a plan for today's lecture. Okay, so what do we mean by an asymptote? Look at the slide here. An asymptote is a line or a curve that the graph of a function approaches arbitrarily closely. Okay, so now I'm going to make a couple of points here. They may or may not make sense to you at this point, at this stage, if you haven't done asymptotes before. But just be patient and give me a couple of minutes. Let me make these points, and then I'll explain these points again with the help of visuals. So let me just first go through these points. The first, as I just said, was that an asymptote is a line or a curve that the graph of a function approaches arbitrarily closely. Now what I'm going to do is, if you look here, I have put this phrase or a curve, these three words, or a curve, in brackets. Okay, so this is basically because you can have asymptotes that are curves, but because we're not going to be talking about these in your syllabus, in your course, we're only going to be talking about asymptotes that are lines. Therefore, we will restrict ourselves to talking about asymptotes, an asymptote as a line that the graph of a function approaches arbitrarily closely. So we have two things here. One is the asymptote, which is a line. And the second is the graph of your function. Okay, so we have to understand how the two interact with each other. What are the dynamics between the two, these two things that we are talking about? The key phrase here is, so to understand how these two interact, or not interact, depending on how we're drawing it. So the key phrase here is the graph of a function approaches this asymptote arbitrarily closely. Now, what do we mean by this? What do we mean when we say that you're talking of a line that the graph of a function approaches arbitrarily closely? This basically means that as a graph of the function heads towards infinity, either or even minus infinity, either in the direction of the x-axis or the direction of the y-axis or in any general direction, then the distance between the graph of the function and the asymptote becomes smaller and smaller. It tends to 0. Okay. Now, some of you may have already got this question in your mind, because this is typically a question that my students would ask in class. So, so the question that may have cropped up in your mind at this point may be that, okay, so could you have a graph of a function intersect with an asymptote? So here the short answer, the quick answer here is yes, there are situations where you might see intersections, where you will see intersections. In fact, the definition of the asymptote has also changed over different periods of time. And if you look at the history, the word asymptote is derived from the Greek word asymptotos, which means non-intersecting. But do remember that this is something we'll be modifying as we proceed along in this course, because to take this as non-intersecting may be a bit misleading. So yes, we can have intersections, but as I said, this will be subject to certain qualifications, and the ultimate test here will be that we have to follow the mathematical definitions of the asymptotes as given in this lecture or as given in textbooks. So we have proper, precise mathematical definitions to go by, and we'll follow. Ultimately, those definitions, the tests have to be passed. So let's move on and take a look at a couple of visuals. Let me show you a couple of visuals to give you a sense of the different points that I just made in the previous slide. Now, in this first illustration, the graph of the function here is given by this curve in blue, okay? And here, in this particular picture, in fact, both the y-axis, which you can see I've highlighted in red now, and the x-axis, both the y-axis and the x-axis, they actually act as asymptotes. Let's just see how. So, first of all, the y-axis is a vertical asymptote, and the x-axis here is a horizontal asymptote, okay? Now, the question is, why would the y-axis, how do we say that the y-axis qualifies as an asymptote? So let's bring our definition, the definition that we talked about in the previous slide, that the graph of a function comes arbitrarily close to the asymptote as the graph heads towards infinity or minus infinity. And let's see what this means. So basically this means that the distance between, so if I take the distance, if I move vertically along this, so because I'm talking of the y-axis as the vertical asymptote, if I move vertically along this graph, then look here, the distance between the curve in blue and the red line, look here, as I move vertically along the graph, this distance becomes smaller and smaller. Now, you can also think of this distance, if you want to be precise, you can think of this, this as the perpendicular that you drop from the curve, the blue curve, onto the red line. And you can see that these perpendiculars, they become shorter and shorter. So, in this sense, we say that the y-axis qualifies as an asymptote. So do you see how we've applied the definition? That the distance between the graph of a function and the asymptote tends to 0 as the graph heads towards infinity. Now look at this x-axis and how this qualifies. Let's see how this qualifies as a horizontal asymptote. Again, if you look at the distance between the curve in blue, our graph of the function, and our proposed horizontal axis, horizontal asymptote, which is the x-axis. So you can see here also that the distance between the graph and the asymptote becomes smaller and smaller as we move horizontally along this graph and away from the origin. The distance becomes smaller and smaller, right? So the distance tends to 0. Yes, in this case, you don't see the graph touching the axis anywhere, okay? So this is as far as the first illustration goes. Let's now look at the second illustration. The graph here is given in black, okay, the graph of our function. And here you can see that we have this horizontal line. Because it's a horizontal line, it's going to be specified by the y coordinate. So we're calling it y equal to some constant a. This horizontal line qualifies as a horizontal asymptote, and here again you can see that the distance is becoming smaller and smaller. It's tending to 0 as we move, as x tends to infinity. Okay, so what is happening here? In fact, to give you a parallel between what you see in this graph and, just to give you some real life parallel to make things interesting, you can actually think of this as a learning curve. This is what psychologists look at, for example, or you could even think of this in terms of diminishing returns in production theory. So let me give you some perspective. So let's suppose in the x-axis, let's suppose x here represents the number of hours that you put in to study for an entrance exam, let's say, and on the y-axis you have you're measuring your performance, which could be in terms of the score that you get on some standardized test that these days you have access to standardized tests to practice for your entrance exams, so your score is reflected on the y-axis. Now, what this graph is telling you is that as you put in more and more hours of work, your marks do show an improvement, but diminishing returns are setting in. You're not able to, like, the increment in marks at every successive step, the marks are increasing, but they're increasing by less and less, and the marks finally level off. Right? So do you see for a far enough distance from the origin as you move horizontally along the graph, so the marks level off. Here also you don't, in this case you don't touch A here. So you don't reach this probably your ideal, but your marks are leveling off just as you can see here, like at this, the graph is flattening off. So this is a kind of a learning curve that you could think of. Okay, so this illustration here, this is to show you that yes, you could have intersections. Now, if you notice here, you have this horizontal line, which I've shown, this dashed line. This is intersecting with the graph of the function, which is shown in blue here. Now, you can see that this is, if you see where my pointer is, this is the point of intersection between the graph and the line. But let's see what happens on or as you move away from the origin, either as x tends to infinity or as x tends to minus infinity. What do you see? As you move towards the right as x tends to infinity, this line, whether you move towards the right as x tends to infinity, or even if you move towards the left as x tends to minus infinity, this line behaves convincingly as a horizontal asymptote. You can see that the distance between the graph and the line is becoming smaller and smaller. As you move farther and further to the left, the distance between the graph and the line is becoming smaller and smaller, tends to 0 as you move as you move larger and larger distances towards the right. So here, even though you have a point of intersection, you have this horizontal line, which does qualify as a horizontal asymptote. And we will give you a precise mathematical definition, which you can then see will fit here. This is another illustration that I have to show you. So I showed you one point of intersection in the previous picture. Now you have a new picture here. Okay, here you have 1, 2, and 3. You actually have 3 points of intersection. This is actually the case of an oblique or a slant asymptote. Okay, so here also you see intersections, but what is nice about this graph is that if you notice, the amplitude of the wave becomes smaller and smaller. If I'm using my physics term correctly, basically your oscillations are getting less and less wilder, and then they just the graph tends towards the oblique asymptote. Basically, we are saying here that if we look at the distance between the graph of the function, which is shown here in yellow-green, and the oblique asymptote, the distance as x tends to infinity, it tends to 0. And finally, I have this illustration for you where I have shown you an asymptote which is a curve. So if you look at this graph here, this curve, which is actually y is equal to x squared, this curve in yellow, this is actually acting like an asymptote. You can apply the same definition that the graph comes arbitrarily close to the curve, right? And this is also acting like an asymptote, but because this is not part of the course, we'll only be looking at asymptotes that are lines, so we will not be venturing into this further, but I thought I'll show you at least one visual for an asymptote, which is a curve. And now we'll start with the first part of our discussion, which is a vertical asymptote. So what is a vertical asymptote? So as the word vertical suggests, it's a vertical line. This is something which is going to be parallel to your y-axis. And because it is parallel to the y-axis, it's a vertical line. So this vertical asymptote is specified in terms of the x-coordinate. Okay, so a vertical asymptote has a form x equal to some constant a. And a line x equal to a is called a vertical asymptote of the graph of a function f if, now this is a criterion that you have to keep in mind. So when does a line x equal to a become a vertical asymptote? It is a vertical asymptote if the function f of x tends to infinity or minus infinity as x approaches a from the left or from the right. Okay, so basically your function increases without bound or decreases without bound as x approaches a either from the left or from the right. Now, what does this mean exactly? And I'll show you some visuals to put this definition in place and to fix this definition in your minds. So basically, let's first get a working sense of how we're going to use this definition. Basically, we are looking out for a line x equal to a such that the function increases or decreases without bound. It just shoots off to infinity or just shoots off to minus infinity. Basically, here we're looking at a situation where the limit, either the one-sided limit or the two-sided limit or both, they don't exist. Okay, so the working definition of this, how will you actually get a vertical asymptote, is that you will this will correspond to basically the zeros of the denominator that you will have in your function, and then once you put the denominator equal to 0, you will see, don't forget this second part. So first you'll put the denominator equal to 0, and then in the second part you will see whether the function tends to infinity or minus infinity for that particular value of x where the denominator is 0. So basically vertical asymptote will correspond to the zeros of the denominator in the function. Now let's see how this works. The first function that I have taken up here in this first example is f of x equal to 1 by x squared. Now, if you look at the picture here, and actually this lecture, the highlight of this lecture is that we have plenty of visuals. It's just full of visuals so that you're able to absorb the content better. Now, if you look at this function, this is a function where as x approaches 0, whether it approaches 0 from the right or from the left, because you have an x squared in the denominator, so that's why it does not matter. So whether the function approaches, whether x approaches 0 from the right or from the left, the function shoots off to infinity. Do you see that? Do you see that in the picture here? In both the first and the second quadrants, a function is increasing without bound as x tends to 0 either from the left or from the right. Basically, you are talking of a situation here where the limit does not exist. And in this case, we say that x equal to 0, which is nothing but the y-axis, this is our vertical asymptote. So if I were a student, what would I have done? I would have actually done this as a first step. I would have seen what are the zeros of my denominator, which would here correspond to x equal to 0, right? This is where the denominator becomes 0. And then I would ask myself, what happens as x tends to 0, right? Because here we are talking of the graph approaching a line. So what happens as x tends to 0, then in this case we have that the function tends to infinity from both sides. Let's take another example. F of x is equal to 1 by x. Now here you can see that the function tends to infinity as x tends to 0 from the right, yeah, but it tends to minus infinity. That's all right. The point is the limit does not exist, and as x tends to 0 from the left, and you can see here, because as x tends to 0 from the left, you'll get a negative number, so the function tends to negative infinity, decreases without bound. So here also we have that x equal to 0 is our vertical asymptote. I'll walk you through two, three more examples. In this example, 1 by x minus 1. See here, if I put x equal to 1, you get the 0 for denominator, and as x tends to 1, you can see whether, so if x tends to 1 from the right, you're going to have the function shooting off to infinity, and if x tends to 1 from the left, the function will tend to minus infinity. So here in this case, the vertical asymptote is x equal to 1. Okay, now what I'm going to do is, at this point, we'll take a little bit of a break, and we will talk about vertical asymptotes again. But I would like you to think about this particular function. So f of x is equal to x squared minus 25 divided by x minus 5. And suppose I ask you to find the vertical asymptote of this function, if it exists. And again, I'm saying if it exists because you may not always have the denominator being, there can't be always situations where you can get a 0 in the denominator. But so for example, if you have, let's say, x squared plus 1 in the denominator, you can't possibly put it equal to 0. So in this case, if the vertical asymptote exists, then I would like you to ask yourself what that vertical asymptote will be, or what if there's more than one vertical asymptote, what they will be. Okay.